Hello, y'all. Daryl Lee Berry Jr. back with some more thermodynamics, continuing where we were last week. Uh, See, I have some stacks, the cooling stacks from a power plant as the background, fitting for the thermodynamics discussion. Um, I've already started on this section. I'll review what I read so far in passing, like I started reading it at the start of my right before my thermal class today. And again, I'm a little bit behind the class because I knew I wasn't going to be on the next exam, so I'm catching up now. So basically, before we learned about partition function, Boltzmann factor. Uh, we actually did some problems from the section one, where we found the probability of um, running into a certain particular macro state of a system. On my other channel, I did a sort of overview of macro state, macro state. You can check that out on my other channel. Here we'll go into more detail about the average value. So this section started with a review of the fact that the probability of a particular macro state is going to be 1 divided by the partition function times the Boltzmann factor. The Boltzmann factor is this exponential, which is the energy of that particular macro state with a negative divided by Q over T, divided by K times T. It is called K times T beta. And right now, I'm working on an example with an atom, which they're saying that the atom just has 3 possible states. One state with 0 electron volts of energy, one with 4, one with 7. And then they actually upped the ante and said, well, we have 5 such atoms. And those 5 atoms, 2 of them are in the ground state, 2 of them are in the 4 electron volt state, and 1 is in a 7 electron volt state. So to get the average energy, we could just add up all the energies and divide it by how many particles we have. And when you do it that way, it's basically this right here. Adding up the energy of each particle and dividing by the number of particles. So 7, 11, 15 divided by 5, that's 3. But that ends up being the same thing as counting up the number of particles with a certain energy. Hey, what's going on, Cygnus? How you doing? Doing some thermodynamics, getting a bit more in depth on this channel. Let me know if you have any questions. So continuing from what I did last week with partition functions and Boltzmann factors, basically getting probabilities of systems that are a lot more complex than just an Einstein solid or a paramagnet or what's another one we did? There's a third one as well. Should be in my notes. The third other common system. I don't remember where I noted it. Maybe I noted it in my actual notes for the last stream. So we're basically taking this particle, or 5 of these particles, with these energies. Average is just adding up the energy of each particle, dividing by the number of particles, which are 5. Same thing as counting up the number of particles with a certain energy and recognizing that's the probability. 2 out of 5 has 0. 2 out of 5 has 4. 1 out of 5 has 7. And of course, this is considering that there's a reservoir that has a certain set temperature. We have the system of these 5 atoms, and we're assuming that the system is in equilibrium with the reservoir, so that since they're in equilibrium, every microstate has an equal probability of arising. So since each of these macrostates have equal probability of coming to fruition, there's 2 of this particular macrostate. So it'll overall, that macrostate will be twice as probable. The macrostate being the overall state of 0 energy and the macrostate being the particular way that can come about. So here we have this. We have the probability of each one. multiply by the energy of each one, and that still gives you the average of 3. So this would be equal to 0. This would be 8 out of 5, 7 out of 5, which is the same thing we have here. 8 out of 5 plus 7 out of 5, that's 15 out of 5, 15 out of 5, so that's 3. And then I went ahead and rewrote it here as the average energy is the, I don't know why this has been happening lately. Maybe it's going AFK or something. So I rewrote it like this. This is the average energy of the system. We have the probability of a particle having 0 energy times 0 energy, probability of a particle having 4 electron volts times 4 electron volts, probability of a particle having 7 electron volts times 7 electron volts, and that gives us the same average energy of 3 electron volts. So this where we're at so far, and I'll keep on going from here. All right, so that was this equation 6.15. In this expression, the energy of each state is multiplied by the probability of that state occurring in any particular atom chosen from among my sample of 5. Those probabilities are just 2 over 5, 2 over 5, and 1 over 5, which is this right here. And I like how they write this 5 hypothetical atoms distributed among 3 different states. So the energy is increasing as we go up, 2 on each rung, and then 1 on the last one. And now I'm in new territory here. It's not hard to generalize this example into a formula. If I have a large sample of n atoms, and ns is the number of atoms in any particular state S, then the average value of the energy is, right? So we're basically generalizing what I have here. So basically I have uh, technically, I guess they're going here. So we have the number that have 0 electron volts times E of 0 electron volts divided by N, which is the number of particles 5, plus the number that has 4 electron volts times the energy 4 electron volts divided by the total number of particles. And let me know if you have any questions, Cygnus. I'll see if I can help. We have the number of particles with 7 electron volts times the energy of 7 electron volts. The number, all right? So if I were to simplify this a bit farther, what they're saying is we have the sum of the number of particles uh, of a certain, or in a certain state, the energy of the particles in that particular state, and adding up all the different states divided by the total number of states. And this is similar to what we did before. This is the sum. So going now to this line here, the sum of all the probabilities of each individual state times the energy of each individual state. All right. So basically the ES, at least the NS divided by N is the probability. And this is NS and this is N. All right, easy enough. And this is equation 6.16, where PS is the probability of finding an atom in state S. So the average energy, and I'll make this one blue as well. So the average energy is just the sum of all the energies weighted by their probabilities, right? Simple enough. In the statistical mechanical systems that we're considering, each probability is given by equation 612. All right, let me rewrite that. The probability of any state in terms of partition functions is inverse partition function times the Boltzmann factor and V is going to be the sum of all Boltzmann factors. And B is going to be 1 over the Boltzmann constant times the temperature. I believe I have that right. 1 over Z F B is the sum S E S and B is 1 over KT. All right. Actually, let me convert these. I'm going to go through later and capture all these equations so I can add them to my formula sheet. So my formula sheet is pretty busy right now. So we're able to make our own formula sheet and bring it to the exams with us. So now I have basically the formula sheet of all 3 initial exams and the new stuff we're learning that's going to be new to the final. So it's getting quite busy. I mixed up which one this is. Let's be a lowercase. All right, there we go. All right. And did I miss a formula? I don't think I did. Got that one. Uh, just got that one. Do believe I got that one up here. Maybe I missed it. But you know what? I converted some of these into homework problems that I did. So that's what I'm remembering. I remember I converted some of these already, but it's in a homework problem. I will be back to do some problems. I'll do some reading right now, and I'll come back later to do some problems. All right, so at this line here, suppose though that we're not, hold on, left off here. Notice that the sum is similar to the partition function, 613. Hold up, what did I leave off? In statistical mechanics systems that we're considering, in the statistical mechanical systems that we're considering, each probability is given by equation 612, which is this right here. So the energy, the average energy, all right? So we're saying the average energy is the sum of all the probabilities of each state times the energy of each state and substituting for the probability of each state. is the sum of the partition function inverted, e to the negative beta es, and the energy of each state. So that's what they have there, even though they wrote it in the reverse order that I did. And it looks like they brought the partition function out since it's not sum, since that itself is a sum. And we have the sum here. And I'm going to have to change the settings on my, I think they must have automatically changed the setting there or something. Let's see if I can do something for this. I'll worry about that later. I'm pretty sure that's what it is. Every so many minutes it goes, my pad goes AFK, and then it, times out. But it seems like it should be some kind of um, feature automatically that if you're screen sharing, it doesn't like time you out. But uh, I'll look at that later. The 1 over z, the sum of the energy they're putting first, and then the Boltzmann factor. All right. So I imagine we're going to be calculating some average energy soon. Let's see how this captures it. Oh, that went pretty nicely. Notice that the sum is similar to the partition function 6.13, but with an extra factor of es in each term. All right. I wouldn't say it's, I mean, I guess it is similar. I mean, this is the partition function here, the one I have in the box right there. Um, I mean, it is similar. When we do actually have the partition function itself in it plus the energy, but other than that, it is pretty much the same. And it gives us an asterisk. In this chapter, we set the system. In this chapter, we set the set of systems that we average over will be a hypothetical set whose members are assigned to states according to the Boltzmann probability distribution. This hypothetical set of systems is often called a canonical ensemble. In chapter 2 and 3, we instead work with isolated systems where all allowed states have the same probability. A set of hypothetical systems with that trivial probability distribution is called a macrocanonical ensemble. So I remember these terms from my modern physics class. So basically, canonical ensemble has a reservoir, and microcanonical is isolated. So it's not necessarily that uh, the same probability of all states changes necessarily. It's just that with the canonical ensemble, now each microstate has the full range of states of the reservoir to balance against. So basically, each state in the system is multiplied by the number of microstates of the reservoir. So the average value of every other variable of interest can be computed in exactly the same way. If the variable is called x and has the value x of s in state s, then the average value of x equals the sum s x s probability s equals sum s x s 1 over z e negative beta e s. 6.18. One nice feature of average values is that they're additive. For example, the average total energy of two objects is the sum of the individual average energies. Okay. This means that if you have a collection of many identical independent particles, you can compute their total average energy from the average energy of just one, if they're all identical, and then just multiply by n, simply by multiplying by how many there are. That makes sense? Right. I've already started working on revamping my formula sheet because I know I might have to um, rearrange everything in it. This is giving us a lot of new formulas. So the professor was really good, and he wants us to learn. He half, roughly, I guess exactly half of the test will be uh, problems from previous exams. He's not going to tell us which one or which type. They'll be similar. He does change the problems a bit. But at least we know exactly what to study for the one half of the exam, but the new exam will be the new other second half will be all the new stuff. So now you see why I've been using the symbol E for the energy of the atom. I've reserved U for the total energy of the much larger system that contains E. So when I divided things into an atom and a reservoir in the previous section, it was partly just a trick. Even if you want to know the total energy of the whole system, you can often find it by concentrating first on one particle in the system, treating the rest as a reservoir. Once you know the average value of the quantity of interest of your particle, just multiply by n to get the total. Okay. Technically, the UN equation 6.19 is merely the average energy of the entire system. If even this large system is in thermal contact with other objects, then the instantaneous value of U will fluctuate away from the average. However, if n is large, these fluctuations will almost always be negligible. Problem 617 shows how to calculate the size of typical fluctuations. All right, so that's the first subsection of this section before we get to paramagnetism. I'm pretty sure I have some problems to do out of this section. I'll take a look and see. And if I do, I'll take a break and come back later and do some problems. So let me see here. We'll have 6.17 and 6.18. So looking at the textbook, yes, those definitely fall into this section, and they look like pretty long problems of like multiple sections to them. All right. So I'll be back. I might take a break and get some dinner, and I plan on coming back and doing problem 6.17 and 6.18, and seems like a good enough stream, about 40 minutes. So thanks for those who showed up. Be sure to drop a line, subscribe if you haven't. I'll see you all a bit later.